Okay, lecture 7, measurements. And the motivation for the measurement is actually hardware restrictions. So as we know, in variational quantum eigensolver, we need to measure expectation value of the Hamiltonian. It turns out the entire Hamiltonian cannot be measured. What can be measured are only single qubit Z operators, right? That's why I changed the previous scheme where we have for every qubit its own measurement, and only Z Pauli matrix operator essentially can be measured. So what this allows us essentially to measure, if we are allowed to measure Z's for every qubit, then we can essentially have expectation values for all the Z's, all products of Z's, or triplets, and so on. But that's not the entire Hamiltonian, of course. A Hamiltonian may have x's, y's, and that's a problem. By the way, in this talk, I will be using like a short notation for sigma Pauli matrices, and instead of putting sigma and superscript z x y, I will just use the letters x, y, z and the subscript that denotes the qubit. All right, there are two main papers that my group wrote last year and this year, and they will be mainly followed in this presentation. Also, there are other advances listed here. One of the latest will come up on archive very soon, and you can see what's the latest following these links in more advanced reading. Okay, now let's start very simple measurement problem for a single product operator. Since we only can measure Z operators, question is, if we have just well, say 1 qubit and we need to measure X instead of Z, so what do we do then? Turns out that all you need to do is to rotate the system, since you cannot rotate the measuring device, right? So the idea here is that if you want to obtain expectation value of X operator, you can introduce resolution of identity, because U dagger U is identity, right? So it's not changing anything. And then what this U and U dagger do, they can be selected so that the X is transformed by this inner U and U dagger into the Z. And what will be left is to do this unitary on the system wave function. So by doing the rotation on the system and measuring Z, effectively you measured X on unrotated system. And that's the trick, right? Can we extend this to many qubits? Sure, multiple single qubit rotations can be done. Say we have x1, x2 now, 2 qubits, and we introduce the same resolution of identity, but now our U1, 2, they are products of 2 qubit rotations. Each of those qubit rotations, they turn x1 operator into the z1 and x2 into z2. And then what is left is to rotate the wave function itself. Now, what is the unitary that could do that? For the case where we want switch x to z, it's actually Adamar gate. And then U1, 2 for the 2 qubits would be just a tensor product of 2 Adamars acting on 2 qubits separately. So now, of course, Hamiltonian contains more than one product. And the question is, can we measure, do these tricks with rotations if we have a linear combination of products of operators, right? For example, say we have a Hamiltonian and it has 2 terms, x1, x2 plus z1, z2. Those 2 terms, they commute, so that's great. The reason I know that they commute, there is a simple rule in when you're trying to figure out whether the product of Pauli operators commute with another product. All you need is to count the number of different differences for each qubit. So you see that x1 different from z1, that's one difference, and x2 different from z2, the second difference. And if the number of differences is even, then they commute. If it's odd, then they don't commute. Now, this is our Hamiltonian, and natural question is whether there's such unitary that would rotate this kind of operator that contains unpleasant x operators into something that contains only z's, conserving the number, of course, of the products, right? So we started with two products and end up with two products. We don't want to create, of course, more operators than we started with. Essentially, is it possible to come up with such U? The answer is unfortunately no. If you like to have a local rotation, so if you'd like your U's to be a product of one particle or one qubit rotation, the answer is no in general. But if you allow yourself these U's to be non-local, so they are like acting on maybe two qubits at the same time, then the answer is yes. And the next question you may wonder about, this non-local use, are they easy to implement? And the answer to that question is also yes, if operators that you're dealing with, they commute. If they don't commute, then this use could be quite complicated, and there is no guarantee that the use that you found would be easy to implement on a classical computer, because all these transformations you want to be able to do on the classical computer before going to the quantum, since you want to understand which operators actually to measure on the quantum computer. And for that, you need this transformation to be done on the classical one. Okay, what local unitaries can do, because these local unitaries are cheap. You can just act on a single qubit at a time, and you would want to use them as much as possible. Turns out the local use, the only use of them is to, say, measure Hamiltonians like this, where each term, let's say for two qubits, for the first qubit, if you compare whether qubit-wise there is a commutativity, then you find that for each qubit you have a commutativity qubit-wise. What this means is that you consider an operator for every qubit, so x1 here, and identity on the first qubit here. So they all commuting with each other, x1 with x1 and with identity. The same with y2. They commutes with y2 and with identity on the second qubit. So it turns out then these type of operators, which we call them qubit-wise commuting operators, because each term in the sum, it commutes qubit-wise with the other terms. Then there is always local unitaries that rotate such Hamiltonians into all z's. Essentially, in this case, this Hamiltonian can be rotated into this Hamiltonian, and all the terms can be measured, right? Now, more than that, every U is a product in such situations of one qubit Clifford gates, which are particularly easy. And there is a theorem essentially that says that if you are dealing with the Clifford gates, then they can be performed on a classical computer easily as well. So all these manipulations can be done on a classical computer before you go and measure things that you need to measure on a quantum computer. That's great. Now, how do I find such fragments in the Hamiltonian? How do I find fragments which I can rotate into all z's and which are qubit-wise commuting in the general Hamiltonian like this, which looks messy? Turns out that there is a nice mapping between the Hamiltonians, qubit Hamiltonians in this case, and graphs. So what you can do, you can take every element, every product in the Hamiltonian and turn it into the vertex of the graph that is connected with another vertex if they qubit-wise commute. So for example, this one commutes with that one qubit-wise, because Z1 commutes with Z1, Z2 commutes with Z2, and identities on 3 and 4 commutes with Z4, and identity on on third qubit. But this one does not connect with this one, because on the first qubit, for example, this one has Z and this one has Y. So they're not connected. Now, what you can do with this graph, once you know how to construct it, is to ask the question, what is the minimum number of measurable groups? And the answer to that question is, what is the minimum number of cliques of that graph? So the cliques are really a subgraphs which are fully connected. So what this means is, for example, in this graph, we have this triangle, and all the vertices in the triangles are fully connected. So that's the minimal partitioning of the graph into the so-called cliques, which are fully connected subgraphs. And those sets of cliques we can now measure by turning into all z's. So these are all z's by construct, well, like from the beginning, and these guys can be turned into the all z's by rotating x's and y's into z's easily. So the details are in this paper that we published recently. Now, how good is this scheme in terms of, say, taking the Hamiltonian terms and turning into the measurable groups? So the fewer measurable groups, the better. And here we tried different molecules with relatively small bases. We have up to 36 qubit problems. And the number of terms, since they grow as n to the fourth, it's pretty large, actually. It's like 55,000 terms. And you don't want to measure every term separately. So you're trying to group with this qubit-wise commuting scheme for a minimal clique cover problem, finding these cliques. Turns out that usually the picture that I just shown you before in the graph, where we have average clique of 3 terms, 3 vertices are connected and fully connected. That's a kind of a typical situation, because say every 3 terms are fully connected, and then you can group them together, measure them together. So the reduction of number of measurements you can make using this algorithm is only 3-fold, right? So that's not enough. Of course, if you want to deal with a 50,000 term Hamiltonian, then the number of measurable fragments will be about 15,000. So it's still a lot, and that's still a problem. Now, can we do better? Natural question. And the idea here is very simple. How do we involve maybe commutativity instead of this qubit-wise commutativity? Because commutativity is more general, and also even in the graph language, if you use commutativity relation rather than qubit-wise commutativity, you can connect more pieces together. For example, the same graph as I was showing before, these 2 vertices were not connected on a qubit-wise commutative graph, but if you account for just the normal commutativity, this operator commutes with this one, because again, if you compare the number of differences that they have difference in the first qubit, second qubit is fine, and then they have a difference in the fourth qubit, then you have even number of differences, they commute, even though qubit-wise they don't commute. Now, the key here to use commutativity is transforming commuting into qubit-wise commuting, and then measuring qubit-wise commuting the same way we did it before. And that requires non-local gates, but they are still from the Clifford group, so they are still fine in terms of implementing them on a classical computer. So how does the whole procedure work? We use here some magical unitary transformations, and imagine if you need to find the expectation value of the qubit Hamiltonian, you prepared your wave function with the unitary transformations, right? So then you break down your Hamiltonian into these commuting cliques. So essentially you gather the terms that are commuting together. And then you introduce in this resolution of identities in order to take the commuting groups and turn them into the qubit-wise commuting groups. That's what the unitary operators here are for. So this UN, HN, UN dagger turns into the qubit-wise commuting group AN. And what is left is to transform with these unitaries the wave function, because you need to do that in order to measure a proper function on this qubit-wise commuting group AN. Right? Otherwise, the result would be altered if you just change the operator but don't change the wave function. Okay, so here's some example. Again, if you have, say, x1, x2 plus z1, z2, they commute, but they don't qubit-wise commute. So you need non-local transformations in order to kind of transform them into the qubit-wise commuting set. And then you can measure that qubit-wise commuting set by locally transforming maybe x into z1 and do the measurement of z1 and z2 from this guy. Okay, so the details of how do we build these unitaries that transform the the commuting groups into the qubit-wise commuting group is in this paper. They are using some advanced math and mapping between the Pauli operators and symplectic GF spaces. So I'm not going to go into the details here, but the new scheme to use this more efficient partitioning could be summarized like this. You have your qubit Hamiltonian, you break it down to the commuting pieces. So all the terms in this HN, they mutually commute, but they don't commute maybe with a different HN, right? Then you use these magic transformations in order to transform all the all the commuting pieces in the HN into the qubit-wise commuting piece. And then on top of the normal unitary that goes from the vacuum state into the state that you would like to measure. So that's this part. You add an extra transformation so that you can measure qubit-wise commuting AN rather than the HN fragment. And so that's combining together all the measurements for the qubit-wise commuting terms into the sum, because expectation value is additional, right? So additive, sorry. Then you can create the expectation value of energy and pass it to the classical computer for the VQE kind of cycle to optimize the unitary. Again, this unitary that you use to create the wave function. The unitaries that break down the Hamiltonian, transform the Hamiltonian from the commuting to qubit-wise commuting state terms, that those unitaries stay the same through the whole cycle. All right, so let's see how this commuting terms grouping work. Are they any better than qubit-wise commuting? And indeed, they are much better, because for, say, similar set of systems, up to 36 qubits, if we are talking about, say, 40,000 term Hamiltonian, then the number of groups that you can measure separately is only less than 400. So it's 100 times reduction of the number of separate measurements you need to make if you group all the commuting terms with this algorithm. And generally, it's n-fold reduction with respect to total number of terms. So if the total number of terms generally grow n to the fourth, then the number of commuting groups grows as n cube. And so that's a lower growth. Let me just summarize that due to hardware constraints, which I don't think will be improved anytime soon, not all operators can be measured without extra rotations. Moreover, not all Pauli products can be measured together at the same time. So you need to find some unitaries that, if you want to measure certain products together, rotate those products into the into the sum of all z terms. So now any group of commuting Pauli products can be transformed to all z measurable products using just Clifford gates. This reduces the total number of measurements by a factor of n, where n is the number of qubits. If the group has only qubit-wise commuting products, they can be transformed to all z products using local Clifford gates. This reduces the number of measurements, not much, threefold maybe, so constant improvement. And finding fully or qubit-wise commuting problems, groups, is possible using heuristic solution of minimal clique cover problem and mapping the qubit Hamiltonian to graph connected with the commutativity properties. With that, let me thank you for your attention and leave you with the questions for further discussion.